Let's see an example for cost volume analysis. The owner of an old-fashioned berry pies, S. Simon, is contemplating adding a new line of pies, which will require leasing new equipment for a monthly payment of $6,000. So that's one cost. And a variable cost would be $2 per pie. So to produce one unit of pie, the operating cost is $2. And the pie would retail for $7 each. So that's the revenue per unit of pie. Question part A. How many pies must be sold in order to break even? So this question basically is asking for finding the QBEP, break-even point Q. So try to use the formula that we learned and find the quantity for break-even point. And later on, I'm going to solve for the Q and show it to you. Next question. The next question asks, what would be the profit or loss if 1,000 pies are made and sold? So if Q is equal to 5,000, what would be the profit or loss in a month? The next question, part C, says how many pies must be sold, so it's looking for Q quantity, it looks for quantity Q, to realize a profit of $4,000. So try to find Q for this. So here is the solution key to the problem for part A, part B, part C, and part D. This is typed and it's neat to see and is visible. But I'm going to do every part separately in the next slide. But it's not going to be as neat as this because I'm going to use my stylus. Let's see the solution. Part A asks for how many pies must be sold in order to break even. The break-even point formula is QBEP, the quantity at which you break even. That's equal to the fixed cost divided by R, the revenue per unit, minus V, the cost per unit. We have these values from the question. So the fixed cost is $6,000. So this is 6,000. The revenue per unit is 7, and the cost per unit V is $2. So this is equal to 6,000 divided by 7 minus 2, which is 5. 6,000 divided by 5. So if you solve for this, it's going to be 6,000 divided by 5, which is 1,200, 1,200. So the break-even point quantity is 1,200. That means that you have to produce and sell 1,200 pies in order to break even. That means that at that quantity, 1,200, your profit is 0. That means your total cost is equal to total revenue. All right, the next part. Part B of the question. Part B says, what would be the profit or loss if 1,000 pies are made and sold in a month? So we know the quantity Q is 1,000. So let's see the profit. The formula for profit, that's equal to total revenue minus total cost, which is equal to, the total revenue is revenue per unit R, which is $7. So that's $7 multiplied by 1,000. That's the total revenue minus the total cost. The total cost is the fixed cost. So fixed cost is 6,000 here, minus plus the variable cost, which is unit cost V, which is 2, multiplied by the quantity, which is 1,000. So this is equal to 7,000 minus 6,000 plus 2,000, which is 8,000. So minus 8,000. That is equal to negative 1,000. So that means that we're going to have a loss of $1,000 if we make 1,000 pies and sell. We're going to lose $1,000. We would be able to guess that it's going to be a loss and not profit. How? Because in part A, we figure out that the break-even point was 1200. That means that at 1200 point quantity, we are going to not make any money or not lose any money. That's the profit is zero. So anything less than the break-even point, 1200, is going to be a loss. And 1000 is less than 1200. So we could say that, yeah, before actually we solve for this, we could say that it's going to be a loss. Part C of the question says how many pies must be sold to realize a profit of $4,000. So we want to find Q such that the profit is $4,000 and we are solving for Q. So we know the formula for profit. Profit is equal to total revenue minus total cost, which is equal to total revenue is the per unit revenue, which is R, multiplied by the Q. So that would be R, we have R, that's 7Q. 7 multiplied by Q, we are solving for Q, we don't know what it is, minus the total cost. So that would be minus fixed cost, that's 6,000, plus the variable cost. We have the variable cost per unit, which is $2, and we are solving for Q. So this is Q. And we know that this is equal to actually the profit must be 4,000. So in this equation, we solve for Q. So this means that 7Q minus 6,000 minus 2Q is equal to 4,000. 7Q minus 2Q, that's going to give us 5Q. So 5Q minus 6,000 is equal to 4,000. I'm going to transform 6,000 here to here, so that's going to make $10,000. So 5Q is equal to 10,000. That means that Q is equal to 2,000. 2,000. So it has 3 zeros. 2,000. So the quantity that we need to produce to make 4,000 profit is 2,000. Part D of the question asks for if 2,000 pies can be sold. So Q is 2,000. Q is $2,000 pies, and the profit target is 5,000. So profit target is $5,000. What price should be targeted or charged per pie? So we want to produce and sell $2,000 pie, and we want to make 5,000 profit, and we are looking for price per unit, or that's actually R. What is R? Price per unit. So we can solve for this. The profit is equal to 5,000. So we're gonna write the profit formula. Profit is equal to total revenue minus total cost, and profit is equal to 5,000. So 5,000 is equal to total revenue. Total revenue is R multiplied by Q. Q, we know that it's 2,000, so that's going to be 2,000 multiplied by R. That's what we are looking for, the price per unit, minus the total cost. The total cost is the fixed cost, which is 6,000 plus the variable cost. Variable cost is V multiplied by Q. V is $2. multiplied by 2000. So that's going to give us 5000 is equal to 2000 R minus 4000 um, minus 6000. So that's 3000 R minus 6000 minus 4000. So here, if we simplify, we have 6000 and 4000, that's 10,000. We bring it on the left side, that's going to be 15,000 here. So 15,000 is equal to 2000 R. That means that R is equal to 15,000 divided by 2000. R is equal to 15,000 divided by 2000. This 2000, this 15,000, which is equal to 15 divided by 2, which is 7.5. So the price target should be 7.5. If we charge $7.5 per pie and we sell 2,000 pie, we're gonna make $5,000 profit. Let's see another example, a little bit more complicated. Cost volume analysis when we have multiple break-even points. Suppose a manager has the option of purchasing 1, 2, or 3 machines. Fixed cost and potential volumes are given in this table. So for one machine, the total annual fixed cost is 9,600 and the corresponding range of output is 0 to 300. And for 2 machines, the total annual fixed cost is 1,500. So as you notice here, it's not 2 multiplied by 9,600. It's different. Suppose that you get some sort of discount or when you buy 2. And the output production, the output range is between 301 and 600. So of course you can produce also between 0 and 300 if you just use one of the machines. But the maximum output with 2 machines that you can get that is different from one machine is between 301, which is more than 300 of one machine, to 600, which is double of that. If he purchased 3 machines, then the total annual fixed cost is 20,000. So again, this is not 3 multiplied by 9,600, and it's different. And the corresponding range of output is between 601 and 900. So basically, again, you can produce, of course, less than 600 when you have 3 machines, but the maximum output, which is more than 2 machines, is between 601 and 900. The variable cost is $10 per unit, and the revenue is $40 per unit. So V, a small v here, is $10 per unit, and R, a small r, or R, is 40 in the formula, if you remember. You need to determine the break-even point for each range. So for this, when you have 1 machine, 2 machine, and 3 machines, we have 3 ranges here. So with these 3 ranges, find the break-even point. And part B, if projected annual demand is between 580 and 660 units, how many machines should the manager purchase? So try to pause here, work on this problem, try to solve it, and after you finish the problem, come back to see the solution in the following slides. Here is the solution key to the problem part A. The part A says determine the break-even point for each range. So we have 3 ranges. A range between 0 and 300 output, then you have 1 machine, a range of between 301 and 600 when you have 2 machines, and a range between 601 and 900 when you have 3 machines. So let's do this for each of these ranges, starting with when you have one machine. When you have one machine, the maximum output is something between 0 and 300. So let's find the break-even point using the formula. The formula for break-even point is equal to fixed cost FC divided by R minus V. R is the revenue or the price per unit of sale, and V is the variable cost. So for one machine, we know that the fixed cost is 9,600 for one machine. The revenue is $40 and the variable cost is $10 per unit. So that's 9,600 divided by 40 minus 10, which is 9,600 divided by 30, which is 320 units. So for one machine, the break-even point is 320. But remember that for one machine, the range is between 0 and 300. So the maximum that you can produce is 300. And that's actually less than 320 that we computed here. That means that we don't have break-even point for one machine. The one machine, whatever you produce between 0 and 300 is going to be a loss. So let's do the analysis for when you have two machines. If you have two machines, we're gonna use the same formula. Break-even point is quantity is fixed cost divided by revenue minus variable cost. The fixed cost for two machines is 15,000 divided by $40 revenue minus $10 variable cost. That's $15,000 divided by 30, which is 500 units. So the break-even point quantity for two machines is 500. And remember that the maximum output for two machines is between 301 and 600. This means that this 500 break-even point value is within the acceptable range for two machines. So it means for two machines, we have a break-even point. This is the break-even point for two machines. This is the QBEP for two machines. So now let's do the analysis for the third scenario when you purchase three machines. For three machines, the break-even point quantity is the fixed cost, which is 20,000 divided by $40 revenue minus $10 variable cost, which is 20,000 divided by 30, which is 666.67 units. And the maximum output for three machines is between 601 and 900. So this is again within the acceptable range for three machines. So this is going to be break-even point for three machines. So our analysis showed that for one machine range, we don't have any break-even point. It's all loss. For two machines, the break-even point is 500. For three machines, the break-even point is 666.67. Now let's see the solution to part B. On the first chart on the left, you can see the total cost in shown for the three ranges for one machine, two machine, and three machines. As you see here, the total cost is going to incrementally increase when you have different machines, or if you have one machine, two machine, and three machines. The second chart on the right, this shows the break-even point for the three ranges that we have. So it shows the total cost and the total revenue. For the first machine, the production is between 300 and 0. So this is the range. And as you see here, the total cost, this line, never going to be crossover or intersect the total revenue line, as we notice, because there is no break-even point for the first machine when you have one machine only. For two machines, the output is between 300 and 600. So it's going to be this range. And as we computed, there is actually a break-even point. And you can actually see it here. This is the total revenue line, and this is the total cost line. which is going to get this intersect here, crossover. That's the break-even point for 2 machines as we computed. For 3 machines, the output is between 600 and 900, the maximum range. And as you can see from the break-even point part chart here, the total revenue is this line. That's going to intersect with this total cost line at this point. This point is the break-even point as we computed. So for 3 machines, we also have a break-even point. So let's now go to the question part B. The question part B says that if the estimated demand is something between 580 and 660, how many machines should the manager purchase? So the demand is between 580 and 660. With 1 machine, we cannot meet the demand. And also 1 machine, as we computed, it doesn't have break-even point, it's all loss. So if the manager purchased 1 machine, he's not going to meet the demand and he's going to lose no matter how many produce. So that's not, of course, a good option at all. How about 2 machines? So for 2 machines, the output is between 300 and 600. And we have a break-even point here. The break-even point is, as we computed, was 500. So the break-even point was 500. And since 500 is less than 580 and 660, 500 is less than these. That means that the demand, that the amount that we're going to produce is going to be 580 to 660, which is greater than the break-even point. So we're going to make money given the demand, 580 to 660. We're going to make money, so that's going to be a good choice. So the manager should purchase 2 machines. Why not 3 machines? Let's see why. With 3 machines, the range is between 600 and 900, the maximum range. And as you can see here, we computed the break-even point. This is the total revenue and this is the total cost. The break-even point is more than the 660. 600 as actually is the break-even point was 666. So that means that if you produce and sell less than 666.6, which is 667, if you produce less than and sell less than that, you're going to lose money. And because our demand is less than 666, that means that if the manager purchases 3 machines and meets the demand, he's going to lose money no matter what, right? So that means that 3 machines is not a good option. So the only other option is 2 machines, to purchase 2 machines.